infinity to infinity, and I have one exponential term. This one. So if you see something like this, anything come to your mind? How should you choose? If we try to do numerical integration, how should you choose your x? And try to see this part. Gaussian. Thank you, Jian. So let's see this page, right? Okay. So of course, this one tells us what is the dimension. So dimension is 2, right? So which means this is 2. And we have some exponential term, but we don't have this part. But this part is not too hard to add it, right? We can try to multiply and then divide it by that. Then we can always have this kind of terms. Okay, then the question is, can you tell me what does this look like? Which kind of Gaussian random variable should have this part as part of the density function? Okay, so we know this is negative, okay, 1/2 T transpose times sigma inverse times T. So let's just try to think about, okay? Think about the case like for this one, if I try to write something similar to this case, so we can write, say, we have x is x1, x2, of course, as a column vector, then x transpose times some sigma inverse times x. This will be x1, x2 times some sigma inverse times some x1, x2. How can it just be, okay, if we get rid of that 1/2, then we will get this is x1 squared plus x2 squared over 2. This is what we have here. Then what does this tell us? So can you find the property of this sigma here? If you consider is the identity matrix, okay, the sigma inverse, then you will get x1 squared plus x2 squared. And then what can we tell? So this tells us actually the sigma here, sigma inverse, is this, right? It's kind of like 1/2 times the identity matrix. Multiply 1/2. Is that okay? Does that make sense? So just think about if you replace this one by identity matrix, then we have 1, 1, 0, 0. So do the matrix multiplication, then you will get x1 squared plus x2 squared. But we have 1/2 here. You can consider you still do the identity matrix, but you have some constant factor, so that's 1/2. Is that okay? All right. Okay. So if you don't have any other x1 times x2 terms, which means this part should be 0, right? And we only have the coefficient just you can consider is at the diagonal. Does that make sense? Okay. Okay, sounds very quiet. So let's just do some other stuff. Let's consider we have a matrix A. Okay, and then I try to use x1, x2 multiplies this xa, or let's do it like this. Okay, you will have is this times that. That's the first part. So you will have ax1 plus c times x2. Okay, this is first term. And then b times x1 plus d times x2. And then x1, x2. And then you will get the term is ax1 squared plus c times x1, x2 plus bx1, x2 plus dx2 squared. So combine it. Okay. But if we go back to check the answer, we know this is exactly equal to what we have here. So which means it's 1/2 x1 squared plus 1/2 x2 squared. Then b plus c is 0, and a plus d is 1/4, 1/4. Then you will argue, can b and c be negative value here? Okay, so one positive, one negative. But this is our covariance matrix, so this should be symmetric, like when you try to construct that. So we won't have that case. So if it's symmetric, it's B0, so we know that's 0. So that's why we know the covariance matrix, the inverse will just be something like that. Okay? Is that okay? So if you see just a quadratic term, due to the property of the covariance matrix, you know this are only have the diagonal parts. Is that okay? All right. So I know this is 1/2, 1/2. Okay. I know this is 1/2, 1/2. Then I can actually consider what is its inverse. So what is the inverse? That's the covariance matrix. So it should be 2 times I. Is that right? Okay. So we have this is 2 times I, then it will be easy for us to know how can I try to do a decomposition, or like it's just 2022, like 2002, like this. So we have that, and then of course, if we just consider, say, to generate some x, okay? So this will be part of the density function of some normal distribution with mean 0, and then with the covariance is this sigma. Okay, then the question is, how can we try to play with that? We know if we have the whole density function, then we can try to use the idea here, do some calculation, then everything actually can change to some simple one. So that's why let's just try to multiply 1 over this and then multiply itself one more time. So because this is 2D, so we try to construct a density function. Actually, is the PDF of this normal random variable. Okay, so let's see. So we know this one. Exponential. We need to divide by 2 pi whole thing square. Take the square root of that. That's because of 2D case. And then we should multiply the determinant of the covariance matrix. So let's consider what is the determinant of this covariance matrix? It's 4, right? But it's the square root of that, right? So it will be 2 times 2. Okay, why? Because we know the determinant of sigma is 2. So square root determinant of, this is 4, sorry. Square root of that is 2. So we divide by 2. And then after we try to divide it, then of course we need to multiply 2 times 2 pi square and take square root, then that's 2 pi dx1 dx2. Is that okay? And then we know this part actually is the PDF of this is vector and sigma. Sigma is 2, 2. Okay? All right, then how can we try to solve this problem? Then we need to do a decomposition of this sigma, right? Can you tell me what is A? What is the matrix of A? Actually, if it's diagonal, it's very easy to do that. Very good. Just take the square root of that. Okay, then we can get this. So for this one, so sigma is 2, 2, and we can consider if sigma is A times A transpose, then for this one, A is just the square root of this sigma, so you just take root 2, root 2. This tells us if we have some C, okay, let's do C, follow the standard normal distribution with dimension 2, then we try to construct this X, okay? One. So we know X actually is A times this C, which means you use this to multiply your C1, C2, if each of them follows the standard normal, and then actually you will get this case. Is that okay? All right. Okay, then the original integration. Let's see this part. So this is X, and we try to use root 2 Z1, root 2 Z2 plug inside, but don't forget this 2 pi. And actually, we don't need to do any other transformation. If you do the transformation, then anything just cancel out. We will still have this density. We just use this. So let me rewrite that. Okay. So we will have, let me just copy what we original version here, but put 2 times 2 pi inside. Cosine x1 squared plus x2 squared, and then times the density function, negative, I think it's 4, right? Okay, 1/4 x1 squared, x2 squared divided by 2 pi squared times 2. And then this dx1, dx2. Okay, then we try to do the change of variable. Okay. For this case, because both of this z and x come from the normal distribution, so the up and lower limit does not need to change. And this is still 2 times 2 pi. But here, something different. So it will be root 2 c1 square c2. Okay. And we know, like, just based on what we have here, so it will actually change to negative 1/2 c1 square minus c2 square. And then this will be 2 pi, and this 2 is cancelled because of the Jacobian matrix. We will have another term comes in, and then this will be exactly equal to this case because we do the transformation. So maybe I can write it. So say we have another one. This comes from the determinant of the Jacobian matrix, and then this is C1, C2, and this cancel out. So we can check, okay? And then this whole thing actually is the density function of the standard normal with 2D. Is that okay? All right, then we use the Monte Carlo methods here. Okay. So what is our f? This is f. And then we have this is equal to sum f of c. I is from 1 to n. So we have that, and ci satisfied this standard normal distribution. Okay, Montevallo case. Is that clear? I know it may be a little bit complicated, but I think if I show you the example, it will be a little bit clear, not just like have all this abstract term, but it will be easy for you to understand. And this is the answer we try to do. Okay, but if you're asked to do some computational case, then of course you just generate zi, like use MATLAB, rand, and like n dimension, or not n dimension, like the sample size, and d. So here is 2. You can easily generate that. However, if you're trying to do it not by hand, just understand the idea. So suppose you're given some, okay, standard Gaussian random numbers, and you know their IDs. Okay, so for example, our negative 0.5213, 0.6102, okay, I just made these fake numbers, okay, 1.0257, and then another negative 0.1012. Okay, suppose you are given these 4 Gaussian random numbers. How can you try to implement to find one estimator of this mu? Very similar, right? Let's just consider what we did before. Like this is mu hat 2 is 1/2. Plug this di inside. So you will have this is 4 pi. Let's put 4 pi outside. Okay. And this is root 2 times the first one, negative 5213, and this whole thing square plus root 2 times 0.6102, the whole thing square. Okay, another cosine. So you can still consider, say, because they are ID, so you will try to consider pair them. Okay, 2 as one pair, and then this will be your, or like two-dimensional Gaussian or standard Gaussian like random vector, and then the other 2 here. Okay. So root 2 times 1.257 whole thing square. And then sum them up, divide by 2. That's the case. So you will have the answer. Of course, this estimation will be far away from the true answer, but you understand the idea. You know, if you were given 4 numbers, then definitely you can only construct 2 vectors. But if you were given 10 numbers, you can construct 4 vectors. Then you will have its mu hat 4 instead of mu hat 2. Is that okay? Any questions regarding these examples? So why I want to spend a lot of time on this, because numerical integration is one important topic for Monte Carlo methods. You understand how to do that. That's very important, okay? Yeah, and also you will see some similar question in your homework, then you know how to do that. So still, okay, question, why this part does not consider when we try to do the calculation? Anyone can answer this question? Why this part, we don't need it? Okay, because it's the density, okay? Because this is the density function of the standard normal. And when we generate this CI follows this normal. So this part is replaced by this numbers we generate. Is that okay? Because you consider if it's a continuous random variable, like when you try to have the expectation, it will always have one part. Okay, like here. You will have this density function. This one will help you to generate this x, and then you will calculate it's only this f. This is very important because this is the expectation of this f of x. So when you try to use Monte Carlo method to simulate that, you just need to do f of x I. Is that okay? This is very important. Or yeah, of course, try to be clear about this part because this is very important when you try to implement the Monte Carlo methods. Sorry. All right. Yeah. So that's why I want to spend a lot of time on this. And if you still have questions, feel free to ask. This is very important. Okay. Always understand because this integration is as the population means. So you always need one density function. Even though here, if we go back, here we don't have a density function. Actually, we have that because the density function is 1. So we don't need to like write it, okay? But for this case, we have this density function is 1/2. Okay, maybe let me emphasize it. It will be a little bit clear. So here, this is the PDF density function of the uniform 0, 2. That's why we just generate this xi. And what is our f? You can see is 2 times cosine xi squared. So that's the case. Okay? All right. Because of the density function. So it's very important to know what is the density function we want to use. All right, I think I spent a lot of time on this numerical integration because this is important. And so far, what we can do is just our uniform and also the standard normal. But after we learn some ways to generate some other random variables, then maybe you can try to deal with different kind cases. The numerical integration, it will be always easy. Like just consider if it's like the standard uniform, it doesn't need to be always the 0, 1, can on different intervals. Like right now we just play with 0 to 2, but I can also make it a little bit more complicated. Say what about -1 to 1? Or what about -1 to 2? So something like that, not symmetric, like how should you play with that? But if you see some like RD case, then in those cases you will consider to generate the like normal Gaussian random variables. Okay, last time we talked a little bit about options. So far you should have some concept what the idea is. Option actually give you one opportunity to purchase or sell some or stock or at some future time, okay?